Hey everyone, welcome to the Weekly Space Hangout for Friday, June, 24th, 2016. I'm Fraser Cain, publisher of Universe Today, and sadly, this is the final episode of the Weekly Space Hangout for this season. So we're going to be taking 2 months off at this point, and we'll be returning Labor Day weekend shortly after DragonCon. Maybe we're going to do something live with DragonCon? Not really sure. So, this week we got a ton of super cool stories. We're going to be talking about evidence for the volcanic history on Mars, the impact of the Brexit on UK science, a new all-sky meteor network, a solstice full moon, water under Pluto, and what's happening with Blue Origin's 4th launch. Joining us this week, we have got a bunch of our regulars. We've got Morgan Renberg. Hey, Morgan.
Happy Friday.
Happy Friday. We've got Kimberly Cartier. You knew.
Hi, Fraser. Hi, viewers.
And last but not least, we've got Dave Dickinson. Where is David?
We're live.
Where are you, David?
We're live from our Airbnb in Rabat, Morocco. We're here one more night, and then we're going to Casablanca tomorrow.
Well, I give your internet a thumbs up. It's pretty good.
Oh, cool.
Cool, and we have got a very special guest for this final episode of this season. We've got Dr. James Green from NASA's Planetary Science. Dr. Green, welcome to the Weekly Space Hangout.
Thanks for the invite, Fraser. Looking forward to it.
All right, so for everyone who doesn't know who you are and what you do, can you give us a quick intro?
Well, I'm the Director of Planetary Science for NASA. I am the highest government official that lives and breathes planetary science and convinces Congress and the administration of what we need to be doing.
We had a quick chat before the show, and we were talking about sort of who you were in The Martian. And so if people who have watched the Martian movie, read the book, which character was pretty much you in that movie?
Well, within my organization is the Mars Exploration Program, and the head of that program is really who we call the Marsar, and that's played in the movie as Venkat Kapoor or Vincent Kapoor from the book and the movie.
Yeah.
And during the time The Martian was made, Doug McQuistion had retired, and so I was the Marsar. So I was doing double duty, rest of the solar system and planetary too, and then working with Ridley Scott on the look and feel of what he wanted to paint on the screen.
Right. Okay. So if in the future someone from the human spaceflight side has to tragically leave somebody behind on the surface of Mars, it might be your team that is doing the observations of the red planet to see if you can find them.
Actually, that would be correct. All the spacecraft that are there now are in my organization. We've got orbiting right now. We have the Mars Reconnaissance Orbiter. We have Odyssey. We have Maven. And we also have Mars Express, which we have some experiments on. It's an ESA mission. And then India has a mission called MOM, which is the Mars orbiting mission. And then on the ground, we have Opportunity and Curiosity.
Yeah, so you've got that planet very well covered. But a planet that you didn't have well covered until very recently is Jupiter. So this is mostly what I want to talk about is the upcoming mission to Jupiter, which starts in 2 weeks. Less.
Absolutely. In fact, this mission called Juno, and it's not an acronym. I think mythologically Juno is the wife of Jupiter, but we're going to get it in orbit around Jupiter on July 4th. So while everyone is enjoying the fireworks, a group of us will be huddled at JPL, listening to the beacon, listening to the engines roar, timing them right down to the last second, and then trying to figure out if it's in orbit or not. And then at the end of that, we'll all be celebrating.
So can we talk a little bit more detail about how this orbital insertion is going to work? So, what is the sequence of events that are going to happen on July 4th?
So as Juno creeps up very close to Jupiter, and in fact, all along the way, it's just put itself just a little higher above the ecliptic. And so as it gets closer and closer to Jupiter, Jupiter is pulling it in, and it will pull it over the northern pole. And as it does that, the spacecraft will reorient such that the thruster is pointing in the direction it's flying. And as it just goes very close to the cloud tops, start that burn, begin to slow it down. We're looking for a 35-minute burn on that engine. We've used it before, so everything looks go for that. The cover is away. The engine is ready to blast. And at the end of that burn, that 35-minute burn, we'll put it into about a 54-day orbit. Then we'll check it out, start turning instruments on after 2 of those 54 hours, and then burn the engine again and get it down to a 14-day orbit. Now, it's a polar orbiter. And it's in a highly elliptical orbit. So when it's really close to Jupiter, it's just above the cloud tops, on the order of 5,000 kilometers. And then it runs way out, well past Ganymede. So more than 25 or so Jupiter radii away from it. We have to do that because what's underneath Juno as it makes these huge pedal orbits is the radiation belt. And that's the killer. So the mission is architected such that we'll have the lowest dose of radiation that we can stand. And after about 32 or 33 orbits, the orbit will precess, end up in the radiation belts, and then we'll figure out how long it can survive in that tough environment.
So can you contrast this mission with the last mission that visited Jupiter, which was, of course, Galileo spacecraft, tragically lost its main antenna array. So there wasn't a lot of high bandwidth coming back from Galileo, and then it, reached the end of its mission. In terms of sort of configuration of the spacecraft, how similar is it to Galileo?
Well, it's a very, very different spacecraft from several aspects. One, the power is quite different. On Galileo, we used radioisotope power. That means we took some radioactive material, plutonium-238. You get it all together into a marshmallow type form, and you look at that, and it just glows red. It's just enormously hot. We have a whole series of those. We stick in a long tube, and then we extract heat with the thermoelectric on one side where the plutonium is, and on the other side, of course, is a voltage drop, which then charges a battery, which then runs the experiment. Juno, on the other hand, will use solar panels. It has the most advanced solar panels I think we've flown in planetary, and it enables us to acquire only 4% of the light from the sun that we receive here on Earth to run the spacecraft, giving it about several hundred watts of power to run the spacecraft and run all the instruments. Now, the instruments are also quite different. Yeah, we've got imagers at different wavelengths, et cetera, just like Galileo did, but primarily we are probing the planet itself. We're looking at the aurora. We're looking at how the magnetosphere interacts with the body. We're looking for the origin of the magnetic field. We're looking for the structure of the body and whether it has a solid or a liquid core. And whereas Galileo, which didn't orbit Jupiter as a polar orbiter, it actually orbited it in the plane of all the moons, was a survey mission. And that survey mission was looking at not only Jupiter, but spending some time flying by the moons and getting a good look at the moons. So this mission is all about the planet Jupiter. Galileo was really all about surveying the entire environment that Jupiter has created.
Great. When do we see the first pretty pictures?
Well, we're going to take a few pictures on the way there. We've used our Juno Cam picture system already as we flew by Earth to get a gravitational assist to then get flung out. But because we have to change the orientation of the spacecraft, we're turning all the instruments off. All attention is on the thrusters. And it won't be until we get into the August timeframe after we get in orbit and start coming back in after, as I mentioned, that 54-day orbit. then we'll start turning the instruments on and pictures will start flowing. And of course, we'll immediately post them to the internet.
Yeah, I can't wait for that. So now, I mean, the way, scientific planetary research really works is that, with each mission, you uncover a bunch of mysteries that then you follow up with the next mission. And one of its jobs is to I guess, resolve some of those mysteries. And of course, it then turns up some more mysteries. So what are some of the big mysteries that you are looking to get answered with this mission?
Well, Jupiter is, of course, our biggest planet in our solar system. It's 317 Earth masses in terms of collecting material early on in the formation of the solar system. And in fact, that is so massive that nothing leaves it. It hardly will have enough energy in its atmosphere to really evaporate away. Now that means it's holding on to everything that it got in the very beginning of the solar system. So by studying how much water it has, by studying at what depth it has, and the ammonia, in addition to understanding its basic structure, whether the core is liquid or has started actually with a rocky core of some point, that will tell us all about where it was formed in the solar system and what was the original elements that made it up.
I know, like, one of the sort of the mysteries that's come up with all of the exoplanet work is we're finding all these really strange configurations of other kinds of solar systems, ones that we would have maybe previously thought were impossible. And so there's this idea that there's some migration potentially going on in these others. How do you get a hot Jupiter? So, some of those kinds of ideas are going to play into this as well.
Well, we already know from evidence that we have that we believe at about 3.8 billion years ago, there was planet migration in our own solar system. And that is indeed a fantastic concept. The concepts that the planets actually moved around and changed their orbits. And one of the reasons this occurred was actually in the early 2000s, a number of the planetary scientists at a conference in Nice, France, we're having all kinds of trouble being able to create our solar system, assuming that all these objects in our solar system were forming where we see them today. They couldn't get them formed. Even after 4.5 billion years ago, you couldn't get Jupiter, Saturn, Uranus, and Neptune formed the way they are today. So one of them decided, hey, well, what we do know is if we move them in closer, they can form faster and the material is there to be formed. So let's do that. And when they did that, they actually uncovered a number of the gravitational resonances that occur, that after these things are formed and after a few 100 million years, those interactions pushes the planets around. So we believe Jupiter was moved inward, and as it did that, it threw out Saturn, Uranus, and Neptune. And when it did that, it took the Kuiper belt, the leftover debris of icy material in the formation of the solar system, and pushed it in. And in fact, I've always said that maybe Ceres is a Kuiper belt object. We have good reason to believe that Triton, a moon of Neptune, is a Kuiper belt object. And so we're starting to put this whole piece of the puzzle together on the formation and the evolution of our solar system. And Juno will have a big effect on our understanding.
Now, you brought it up, so let's talk for a second about some of those other objects. As the Director of Planetary Science, it really is, you're the person who has to cut up the pie. Right now, a lot of that is going to the exploration of Mars. But as you said, Mars has got a lot going on. Now we're back at Jupiter. We've got Ceres analyzed, Vesta, even Pluto. So let's talk about Uranus and Neptune. Any plans to revisit them?
Well, I really dearly love Uranus and Neptune. Only the Voyagers were able to get a good look at them in their flybys. What you may not realize is we've been very methodical in our exploration of the solar system, and we implement first flybys. We then survey what we like to go back to. Then we get into orbit. And after getting a complete comprehensive view of the body. Then we know where to do the third thing, which is land and then rove, and then we want to return samples. This is where we are with the moon. Flyby, orbit, land, rove. We've completed and returned samples. We've completed that. Where we are with Mars, of course, is our early mariners flew by Mars. Our orbiters are there now. We've got rovers. And now our 2020 mission, we're planning to start coring rock and being able to get ready to bring samples back. So we've made enormous progress with that. And in the meantime, as we move out in the solar system, we finally completed that initial exploration of our basic part of our solar system. And what we feel now are all the basic parts, including that new Kuiper belt that we've really uncovered over the last 20 years in greater detail. We now, by that flyby of New Horizons, completed that initial set. Now that tells us we need to go back. It tells us what we need to concentrate on, and Uranus and Neptune are right up there. Currently, I have JPL starting a major study and studying how to get into orbit around Uranus and Neptune. We have a variety of science that we want to do. These two bodies are very different than Saturn and Jupiter. You know, Saturn and Jupiter we call gas giants. They're dominated by hydrogen and helium. But, you know, Uranus and Neptune, we actually call them ice giants. They're dominated by a lot more of the outer realm of materials. So these are ammonias and water and other types of ices. And in fact, as I mentioned during that time of the rearrangement, probably Uranus and Neptune gobbled up a number of Kuiper belt objects along the way, and that also contributed to its current compositional difference. So it's hopefully in the next decade, we will have lined up some really great missions to get out there.
Yeah, I know you have a bit of a soft spot in your heart for those worlds, and especially because we just haven't stuck around. And for me, Triton is just one of the biggest, most interesting places in the solar system. It breaks my heart that all we've got is just these pictures that that Voyager 2 took as it went past, and that's it. Like, what a crazy world.
Well, as I said, we believe Triton is probably a Kuiper belt object. Now, it's actually bigger than Pluto. So,
And it orbits the planet in the wrong direction.
Well, that's one of the reasons why it lends credence to the idea that was captured. But it has a number of icy features on its surface that is very Pluto reminiscent. And I think we're going to see more research being done on that in the future.
That sounds great. Let's talk about some of the other missions that are sort of in the works, but are still, after Juno. What should people be looking forward to in planetary science from NASA?
Well, Juno is flying right now, and we have a couple missions that are coming up that we're going to be launching. And the very next one is called OSIRIS-REx. This is an asteroid sample return. It's going to an asteroid called Bennu. And if you can imagine, nearly a spherical asteroid with a nice little belly band that's about 500 meters in diameter. That's what Bennu is. It's a carbonaceous chondrite. It has probably full of organic material, maybe even amino acids, one of the building blocks of life. We know it's these kind of asteroidal materials that bombarded the Earth early on. And as I mentioned, even during the what we call the late heavy bombardment, where the planets rearranged themselves, and not only the Kuiper belt came in, but also the asteroid belt came in. We believe the Earth had plenty of bombardments from asteroidal material, and that would include these carbonaceous chondrites. So OSIRIS-REx launches. Window opens September 8th. It leaves Kennedy. It runs out to Bennu in a couple years. We'll be actually orbiting that for about a year, or actually a little more than a year, picking a place to sample, getting a sample, bringing it back. But in fact, in 2018, we have another mission, and it's going to Mars. It's called InSight. This particular mission is a platform. It's not a rover. It's going to sit down on the surface. It's actually in the near longitude that Curiosity is in, but maybe 4 or 5 degrees or so at a higher latitude. And it's going to sit down in a flat area. It's going to bore down a couple meters, and it's going to actually measure the heat flow of the planet. The planet is cooling, and we want to know what that heat flow is like. It also has a seismic instrument, the most sensitive seismic measurements ever made by man, sitting on the surface of Mars with this mission. And we're going to see, if Mars rocks. Of course, we already know Mars rocks.
Right.
But, really shakes. We actually see from the Mars reconnaissance orbiters avalanches going on. So we want to know, is that because there's internal shaking that's going on at Mars? Is Mars really alive, so to speak, from that perspective? Or is that due to meteoric hits? Surely Mars is hammered by meteors, just like the Earth is every day. And so we'll get a really good idea as to the internal structure of Mars, because we'll have that seismic instrument. We'll understand the heat flow. We'll also have a weather station that also contributes to our overall knowledge of the circulation, temperature, pressure of Mars's atmosphere.
We got a picture of it. So that's great. I'm really excited about some of the stuff with Europa as well, and some of the longer term missions. But one of the questions that I have for you is that we're starting to move to this place where in the past these missions were all these individual solitary spacecraft sent, and with places like Mars, you're starting to feel like there's this real infrastructure that's starting to get created. There are a bunch of missions. They're communicating with each other. They are in some cases assisting each other. Is this sort of where a lot of the future of planetary science is going to go? We got more and more resources to work with to get more of this science done?
Well, that's a really good question. In terms of Mars, there's specific reasons why we've started to develop that infrastructure. One of which is we have, because of our rovers and anything that's down on the surface, we have to take into account the fact that, Mars is at 1.5 astronomical units away. It's much further away. And so rather than carrying big dishes around, if it had a relay satellite, that would work for us. We also have to have satellites that have the right kind of instrumentation to be able to take high resolution images that will help us land in tight areas, maybe inside craters. That's what we did with Curiosity, is landed it inside a crater called Gale Crater. And so we have to have associated orbital assets to continue to do that. MRO has got, you could see your coffee table sitting on the surface of Mars if it was there. I mean, it's a real spy camera from that perspective. And it needs to be, because that's the kind of level of detail we need to get if we're going to land anything. But in addition to that, MRO has been in orbit for 10 years. Okay, this is its 10-year anniversary in 2016. And it's mapped, get this, only about 3% of its surface at that high resolution. Why? Mars is a big place. And it takes a long time to get high resolution data back to Earth. So we have to be really specific about what we want to look at and get the detailed information necessary for us then to be able to plan sites to go to. Now, one of the things that we've done this last year is we had a call for participation of all our science and exploration communities on where we would put humans on Mars. Where is Ares 1, if you know about the Martian. And it turns out the science community got together with the exploration engineers, and we have about 47 or 48 fabulous sites on Mars that we need higher resolution imaging for us to determine whether they are good places to go or not. And that means we want to study what the resources are. Where's the water? How deep is it? Are we near glacier material? What kind of hydrated sulfates are there, et cetera, et cetera. And so that's gone really well. And over the next couple years, we're going to whittle that down to maybe a half dozen sites. And then we'll know where we're going on Mars.
So I'm going to take, actually, I have one last question for you, and then I'm going to take some questions from the audience. So if you're watching this right now and you want to ask some questions for Dr. Green, just go ahead and put in some questions in there, and I will try and find them. Which is, what are some ideas that are currently in the sort of, I don't know, the initial proposal stage that you find kind of exciting and fascinating as methods for exploration? And I'll give you an example here, which is, I don't know if you heard this sort of the starshot idea where people want to send spacecraft to other stars using lasers and solar sails. We talked about that quite a bit here on the show. But that sounded to me like a fairly interesting way to actually explore the solar system, that not just, why go to another star? What's closer is, let's see if we can, make it out to Pluto in a couple of weeks as opposed to 10 years. So are there some ideas and stuff that people are working on that you think have some really interesting applications in the sort of the future of planetary exploration?
Yeah, there are. And the one that really has got me excited more than anything else is a Europa Lander.
Yeah.
We're now starting to think about getting down on the surface of Europa. Europa is a moon of Jupiter. It's got an ice shell. Underneath that ice shell is twice the amount of water we have on this planet, and yet that body is about the size of our own moon. This is a spectacular opportunity to really study an environment that could have evolved complex life in a very different way than what we have here on Earth, because of the ocean-land interfaces. This has been all ocean interfaces. So consequently, the next set of experiments that we want to go after are life detection instruments. Now, we haven't done that in planetary since Viking. Viking was in 1975. Because we didn't find, actually, it's coming up with its, 40th anniversary of landing in 1976 on Mars on July 20th. So in a matter of a couple weeks, we'll be celebrating that. But Viking had light detection instruments on it, and the concept was, three instruments had to say a thumbs up for life. Then they would declare that they believe they see life on the surface in the soils, and this would be perhaps extinct life, perhaps even extant life, whatever they could measure. But only one of the instruments had some sort of indication of life, that Mars had life. Well, that actually, because there wasn't a positive indication, really set the program back for quite a while. And so we've then taken a more cautious approach, a more methodical approach, going after life right away after just a few flybys and a couple orbiters around Mars was a huge leap. And we now realize that perhaps that leap was too far. But on Europa now, I think we're getting ready with the right kind of experiments on a lander to really look for life. So that's a huge step forward.
Yeah, and either way, right? If we find it or if we don't find it, it is a fascinating question and mystery each way. All right, let's take some questions from the audience, because there's some great ones here. So this one comes from, I lost it. Right, Nicholas of the Yard, which is, any plans to send a microphone to Mars? Come on, when can we listen to the sound of the wind on Mars?
All right, I love the idea. And that will happen. We have them on Mars 2020. This is the mission that's going to get down to the surface. It looks like Curiosity, but it has a new whole set of instruments. It has a drill on it. It's got a GoPro on it, and that GoPro's got sound, and we're going to be bringing that sound back. I, too, would love to listen to sounds on Mars, from the day before. It would be absolutely fantastic. But the sounds not only are important because it will correlate with our wind measurements and other things, we're going to hear the sounds of the rover. We're going to hear the creaking, cracking, all that, stuff that goes on as we move over the rock environment. And so it has an important engineering aspect to it. It helps us, as if the sound changes over time, perhaps that's a developing problem we need to get on, understand, and fix it before we get to the point where the rovers broke for good. So I think what we're going to see from then on is that sound measurements on the surface of Mars will be a standard set of experiments that we will perform.
I can't wait. I know the Planetary Society is really excited about the opportunity to hear that, and I know they've been really lobbying to make this happen, and I'm just going to add my voice to their support. So, if you perhaps know somebody. You hear us, all right. If you perhaps know somebody who perhaps is involved in these matters and can help make those recommendations, I think that would just be amazing. And I get that question all the time, which is like, what is it? What does it sound like? All right, so David Joseph Wesley wants to know, what sci-fi books do you find most inspiring? Favorite movies, TV, books? What should we be watching?
Well, I really, in my early days, loved Dune. I thought that series was fantastic. Read every one of them, and nothing really captured my attention so much since then until The Martian came out, until Andy Weir's book. And I think it's because, I became more professional, became more of a scientist. Built spacecraft, were involved in all that stuff, and so his book from that perspective was really captivating. And so indeed, I think Andy's book is just fantastic, and I really enjoyed it.
And we were talking about this before, the Expanse as well. You provided some feedback to them on that as well.
I did. I didn't know much about the Expanse until they were nearing the end of filming the first episode, and the studio contacted us and said, we'd like to interview Jim and Jim Green and talk about real science versus what they were doing in the Expanse, and said sure. So I saw the first one or two episodes, really enjoyed them, and from many perspectives of the concept of what's next beyond Mars. What is next? We've got all kinds of possibilities, and it's a great idea to play around with scientifically. And so I did a number of interviews where they've used that and put it on the website. But so for my birthday, my daughter just sent me first three major Expanse novels, so I'm ready to read it.
Oh, fantastic. Okay, so this question comes from Larry Beckham. Will Juno end by deorbiting like Cassini? So, and Galileo.
Yeah, right. Our plan is to ditch Juno into the planet. And part of that is because we really don't want it hitting Europa. Even though the radiation environment is very tough for it, we don't expect human microbes at any huge number to be able to survive on the spacecraft. We're not taking any chances. We don't want to infect Europa whatsoever. So we will ditch Juno, just like we will ditch Cassini. Now that's actually going to happen over the next year and a half or so.
I'm not listening. Don't do it. No, I understand. You got to do it.
Well, we have to do it. Cassini's running out of fuel. Yeah, over my shoulder is one of the backlit pictures of Saturn Cassini made, which is just absolutely spectacular.
Yeah, and I'm in that picture, by the way.
Yes, we all are. Did you wave that day or not?
I did. Yeah, yeah, I went up and waved.
Good for you. We'll have to check that out.
Yeah.
But we are in the process of doing a couple really tight swing bys of Triton, and that's going to enable us to change the orbit plane. We're going to get it up to 68 or so degrees in latitude, and that's then going to require a burn for which then we will change the closest approach of the planet to be not outside the rings, but inside the rings and right off the cloud tops. So Cassini's going to be orbiting Saturn in the same way Juno's going to be orbiting Jupiter at about the same time this next year. We will see some spectacular views. Spectacular science done.
It'll be good. It'll be a good way to go. So on that note, just to one final reminder for Juno, before we let you go, if people want to experience the excitement of this live, when should they set their watches to?
Okay, so the burns actually start a little after 8, about 8:18 Pacific Standard Time. And then, as I said, 35 minutes, that burn will go on. And then we'll be getting tones back. Light travel time is 40 minutes. So by the time we start getting the tones, it'll all be over. And we'll follow up with that, see where the spacecraft's at, and hopefully it's a good position for us to be able to have it captured. So this will be July 4th. So on the East Coast, between 11 and 12, when you see the fireworks, that's when all the fireworks will happen at Jupiter.
Wonderful. Well, Dr. Green, thank you so much for joining us at the Weekly Space Hangout. We are big fans of all of the science and the planets and the intersection thereof. So it was great to have you here on the show with us. Thanks a lot.
My pleasure. I've got to run now.
All right. Good luck. All right. So first, while we reconfigured the screens, I just want to say a big thanks to Chad, who's sitting here beside me and has been making this show so smooth. Have you seen that? He's putting up pictures. He's putting up the questions. And the sound didn't cut off. It was fantastic. A big thank you as well to the whole WSH crew, the Weekly Space Hangout crew. These are, of course, the fans / producers of this show. They schedule the guests. They moderate the comments, and they put a bunch of the preparation of the show together. We literally just show up here and talk. And they're doing a lot of the work. So if you want to join them, a lot of places you can go and find them. Just go to WSH Crew. Just search for that on Google, and you'll find the version of the WSH Crew that works for you. So awesome. We're ready to go. Should we move on? Well, let's talk to Morgan then, and then we'll push you to the limit here. So Morgan, let's talk about let's start with Blue Origins.
Yeah, so we've been talking about Blue Origins and SpaceX now for more than a year, and they're taking sort of two diverging paths towards the question of rocket reusability. SpaceX started by launching satellites to space, cargo to the International Space Station, and is now beginning to land the rockets and evaluate them for reuse. On the other hand, Blue Origin has started with a small rocket and has begun launching and landing and launching and landing it, but they aren't going high enough up to launch a satellite or deliver cargo to the International Space Station. So they're planning to make their money through space tourism. They're going to put about 6 people in a small capsule on the top of their rocket, blast them up above the international line of space, where they'll get about 3 to 4 minutes of weightlessness, and then bring them back down with parachutes. Now, of course, we're always putting safety as our highest priority when we talk about spaceflight, but when you start bringing tourists into the picture, you want to ensure an even higher level of safety than you might for, say, a government-sponsored astronaut whose job it is to take the risk of going to space.
Right.
And so Blue Origin this week conducted their 4th consecutive relaunch of the same rocket that they have been using from the beginning. And that launch went off without a hitch, but it did have one intentional glitch in it. And that's when they jettisoned the capsule and it began drifting back to Earth, only 2 of the 3 parachutes deployed. And this was on purpose because they wanted to test and prove that the capsule could still land safely and comfortably, even if one of the 3 parachute systems failed. And it did, and the capsule landed successfully, and everything is good. But I think the bigger story here is a glimpse at what reusability allows us to do in terms of safety for rockets. Because in the past, if you were launching a rocket that cost $100 million or $200 million or $300 million, you didn't have a lot of launches available to test out different safety features. And this is probably most viscerally demonstrated back during the Mercury era, in which they launched Alan Shepard into space after successfully launching 2 rockets without having them blow up. They just didn't have enough rockets, and they were too expensive to build to launch a lot of them to prove reliability. But Blue Origin says it costs in the low thousands of dollars to refurbish their rocket in between launches. And Elon Musk has said that the Falcon 9 burns only a couple $100,000 worth of fuel to launch every time it goes up to orbit. And so for costs like that, a few thousand to maybe a couple $100,000, you can afford to launch your system over and over and over again and test out all of the different possibilities of failure. You can find, what happens if one of my rocket engines doesn't work? Or what if the parachute system doesn't work? Or what if the rocket that's designed to eject the capsule off of the large rocket fails halfway through? You can try all of these different things and prove that you can recover from all sorts of different errors or accidents before you ever have to put a human being on board the spacecraft. And this is just another reason why reusability in terms of rocketry is going to be the future of rockets. And Blue Origin demonstrated that excellently this week.
Check it out. Yeah, this is a step that SpaceX still has yet to do, which is to fuel the thing up and see if it can take off again. And this is the 4th time for Blue Origin.
Right. SpaceX has, like I said, has a different business model than Blue Origin does. SpaceX is actually trying to make money right now, unlike Blue Origin. And in order to make money, they have to put commercial satellites on top of the rocket and launch them into orbit. And so when you have somebody's $50 or $100 million satellite on top of your rocket, then there's a much higher threshold you want to cross in terms of making sure that the mission's actually going to work. Yeah. And so I think SpaceX is understandably more reticent to just start throwing these reused rockets back up there before they're more certain that they're going to function. And I think it probably is likely that we'll see at least one test launch of a Falcon 9 relaunch before we see them try to put any payload on top of it. But I wouldn't expect to see the situation we have with Blue Origin, where they're just launching it over and over and over again empty. Because SpaceX from the beginning has been pretty focused on developing a sustainable line of business that will allow them to continue to fund the development of larger and more complicated rockets.
Yeah, I mean, I think once they move into this place where they can start to have like a discount where you can either launch with a brand new rocket or you can launch with a refurbished rocket, and if they're safe, then over time the economics of it will be figured out. But I know from Musk's perspective, that spacecraft is going to be able to launch many, many, many times. I mean, they've tested the engines, they've tested a lot of the components to do that. So still, it's incredibly exciting to see a rocket take off, fly to space, return 4 times. So with
That's
Blue Origin,
tremendous accomplishment.
Yeah, congratulations to the Blue Origin team. All right, awesome. Let's move on. Kimberly, let's talk about volcanoes on Mars.
Sure. So we were talking a little earlier about the Curiosity rover on Mars. And earlier this week, the Curiosity rover was roving around Gale Crater as usual and was analyzing some drill samples from the bottom of the crater and discovered a very unexpected mineral. Now, scientists at NASA Johnson Space Center, the Astromaterials Research and Exploration Science Group, were looking at these data, trying to figure out what this mineral was, and they realized that it was a silica mineral called tritonite, which was completely unexpected to be found on Mars. Now, tritonite is very common here on Earth because it's formed via explosive volcanic processes that require very high temperatures and very high concentrations of silica material. And now, our current understanding of Mars was that these types of explosive volcanic processes weren't possible in Mars's history. So the presence of a mineral that can really only form through these very high temperature explosive volcanic processes was highly unexpected in such a cold and non-volcanic environment like Mars. So this begs the question of how exactly these minerals got there, whether or not Mars actually had these sorts of high temperature volcanic processes in the past, or if there's some sort of low temperature, less volatile mechanism to form this mineral that we just haven't discovered yet. Now, all the tritonite on Earth, we believe really was formed through volcanism, and we haven't found any evidence that any tritonite on Earth could have formed at low temperatures. So there's no evidence to say that you can, but if we say that there's no other way to form this mineral than through high temperature volcanism, then we really have to readjust our thinking about the evolutionary history of Mars.
Now, of course, we can look at Mars and see the largest volcanoes in the solar system. So clearly there was some volcanoes happening. But I know there is some controversy even about whether there is still active volcanism on the planet at all. Like the question is like when was Olympus Mons' last eruption? Was it millions of years ago, hundreds of millions of years ago, billions of years ago?
That's a very good question that we still don't know the answer to. And we also don't know what kinds of eruptions that volcano could have had. The types of eruptions that cause this particular mineral are the really explosive kind like Mount St. Helens or the Satsuma Iwo Jima volcano. And we just don't know whether or not volcanoes on Mars could have exploded that way. So even if they were, maybe they didn't have a hot enough temperature or enough power to form these minerals. We just don't know.
Yeah. All right, Dave Dickinson. Let's talk about water. Oh, sorry. Let's talk about the solstice full moon. Right. Morgan's going to talk about water on Pluto.
This is an event that it's kind of come and gone observationally, but it was still kind of interesting. There was an interesting discussion on the internet, and I did write about it on Universe Today. We had the summer northward solstice, which is the winter solstice in the southern hemisphere, and it's the summer solstice for the northern hemisphere on Monday, June 20th. And we also had a full moon within about 11 hours of that. Now, there's a lot of discussion of the coincidence of how rare this is, and there was a lot of different news agencies that were saying that it was the rarest in a century. It's really kind of how you slice it, because both the full moon and the summer solstice are really instants in time where the moon is moving from 180 degrees ecliptic longitude, and it's like opposite to the sun. So they're really, if you're looking at it it matters like if you're looking at it in universal time or you're looking at it from a particular time zone, if they're falling on the same day. I did a little bit of looking at this, and it's closest in terms, if you want to say how many hours apart they were for the 21st century. Really, it's a function of what's called the mentonic cycle, which also plays in when you're trying to predict eclipses. If you take the lunar cycles, the synodic periods from phase to phase, from full to full, from new to new, and it's 29.5 days, and you add them up, you can nearly divide them evenly into 19 years. So the whole upshoot of that is every 19 years, you're going to have say, another full moon fall on June 21st or June 20th. You pick 19 years from then. So it's in a category of saying it's extremely rare. I'd be, it's rare in the sense that, and then again, it's the same. If you're looking to say, well, it's winter solstice here, summer solstice in the northern hemisphere, winter solstice in the southern hemisphere. We actually had, a lot of people don't remember, in 2010, a lunar eclipse during the winter solstice, summer solstice in the southern hemisphere just back in 2010. And so you got to figure how rare is that we're having a full moon. You have an eclipse by definition has to happen on a full moon for a lunar eclipse and a solstice at the same time. So it was a neat pairing of the two. Like I said, it's come and gone this past Monday, but there was an interesting discussion that cropped up about, is it rare, is it not?
And what do they call it? They call it a strawberry moon?
The June moon, when you're looking at like the Farmer's Almanac, which draws these from the Algonquin, the tradition of the Algonquin Indians, yes, it was known, the June moon is known as a strawberry moon. I've heard it referred to as honeymoon, strawberry moon. This one, I guess you could call it, was a solstice moon. So
yeah, and this
it's
is
interesting.
and this is when I guess all my strawberries are ready in June.
In the northern hemisphere.
Yeah.
I like to call it the northward solstice to avoid confusion between, because I'll inadvertently, if I say happy summer solstice, I'll get everybody on Twitter in the southern hemisphere saying, well, it's winter down here. So.
Yeah. Remember, we live on a spherical planet, and fully, half the planet has concerns when you make any of those sweeping generalizations.
Try to please everybody. So.
Yeah, exactly. Even though they're upside down. Or are we upside down? Cool. All right, Morgan, let's talk about water on Pluto.
Well, with the flyby of New Horizons, just about a year ago, we gained a tremendous amount of new information about Pluto. And one of the things that we've been able to do with that information now is use it to constrain the physical models that we simulate inside of computers to try to understand what's going on beneath the surface of Pluto. And so by putting in some of the new physical parameters we understand about Pluto, like the ratio of composition between nitrogen ice and water ice, researchers have been able to simulate a new idea about what might be happening on the inside of Pluto. And they did this in search of an explanation for these long cracks we see on the surface of Pluto. We call these extensional cracks, which means that they must have formed due to expansion. And that's not really too surprising because as we all know, when we make ice here on Earth, you freeze water and ice expands. And so if Pluto once had a lot of liquid water in it and you froze it, you would expand that ice, you'd create these extensional cracks. But that led to the question, well, if Pluto had a lot of liquid water in the past, could it still have liquid water today? And the result of this simulation is that, yes, it could still have an ocean of liquid water today, buried something like 280 kilometers underneath the surface. And like many scientific simulations, this one didn't give a single result. It gave two different possibilities for what could be happening at the center of Pluto. On one hand, it could have frozen completely solid through. Or on the other hand, there could have been still a little pocket of water on the inside. But we have pictures from Pluto that will help us answer this question. Because ice is weird. Water ice is extremely weird. I just said that when you freeze it, it expands. But if you freeze it under a lot of pressure, like for example at the center of a planet, ice actually contracts. And what that would do is shrink the entire size of Pluto. And if you shrink something, you generate a different kind of crack called compressional cracks. You can see these, for example, all over the surface of Mercury, which we know has cooled and shrunk substantially over its history. But if you look at pictures like this one of the surface of Pluto, there are no evidence of compressional cracks across the surface. And so these researchers interpret this as saying, well, the entire center of Pluto must not have completely frozen. And if it's not completely frozen, that indicates that there must actually be liquid water deep, deep below the surface of Pluto.
And this is one of the ideas, right? That there are reservoirs of water under potentially all of these objects, all of these Kuiper-Belt objects, which then really expands the places that we're going to have to go searching for life. And we've talked about Europa, Enceladus is interesting, Triton, Pluto, Eris, all of them.
There's sort of building a consensus now that you can make a plausible argument for the existence of liquid water at the surface or at the center of any differentiated object. So when you differentiate something, you sink all the heavy stuff to the middle. And that concentrates all of the stuff that generates heat, like uranium, for example. And so if you put all of that in the core of a planet or a large icy object, then you have this very concentrated area of heat that can keep water warm enough to be liquid over the course of billions of years. And that's something we weren't even thinking about a couple of decades ago.
Yeah, and that just really expands the places where we're going to have to send spacecraft. So I hope Dr. Green's taking notes. All right, Kimberly.
Yes.
Next up, the Brexit.
The Brexit. So if you have not been watching the news in the past 24 hours, the citizens of the United Kingdom have just voted by a very slim margin to leave the European Union. Now, putting aside the historicalness of that event. And regardless of where you sit on whether they should have voted that way or not, the Brexit, as it is called, could have very significant implications for scientists in the United Kingdom. These really big ramifications really fall into three different categories, which are the funding situation for science in the UK, the potential for mobility for scientists and students in the UK, and also how the UK will be participating in a lot of the collaboratory multinational scientific efforts like CERN and the European Southern Observatory. So going back to the first point, which is the financial aspect of it, the European Union has historically contributed a few percent of the scientific funding to the United Kingdom, which might not seem like a lot, but to scientists and postdocs who are looking for grants or fellowships, the European Union is one of the most recognized places to go for that sort of funding. So the political party who was pushing for the UK leaving the European Union did promise to make up for that slight drop in scientific funding, but we'll have to wait and see on whether or not they actually follow through with that promise. Regarding mobility and collaboration, one of the great benefits of being part of the European Union is the ability to travel pretty freely throughout all the countries who are part of the European Union, which is a great benefit towards scientists who collaborate with other scientists in other countries around Europe. With the United Kingdom choosing to leave, one has to wonder how that will impact scientists traveling between countries in the European Union, or members of European Union states choosing to go to the UK to pursue jobs, or even going for university and grad school. As far as being a student goes, being a member of the European Union in the past has meant that if you choose to go to university in the UK, you receive great tuition discounts. And now with UK choosing to leave, those tuition discounts would go away. And so you have to wonder how many students are going to choose to pay the additional cost just to go to a university in the UK, and how friendly those environments will be. Lastly is the participation of the UK in the multinational collaborations like CERN and the European Southern Observatory. It's not a requirement to be part of the European Union to participate in those collaborations, but it certainly makes it a lot easier. And the United Kingdom would have to go through a whole new round of negotiations with these collaborations to become some sort of associated member state so that they could still participate in these scientific efforts.
That's what we Canadians are. We participate in some of those international collaborations, like some of the big observatories, but we're obviously not part of the European Union. So,
right, and a few other countries like Iceland and Luxembourg and Israel, I believe, are also part of these some of these associated states. So they get some special privileges that non-European Union states don't get. But so UK will have to work out those negotiations with each individual collaboration to maintain their current status and involvement in those projects. So I know that before the vote happened yesterday, a large group of UK scientists signed petitions and wrote letters to all the politicians and citizens expressing these concerns of what leaving the European Union would actually mean for the scientific efforts in the UK. Unfortunately, it doesn't seem like their voices were heard to the extent that they wanted. And now we're just going to have to see what the future actually holds for UK science.
Yeah, I mean, as the folks in the UK have now voted for something that, as you said, is sort of historic in scale, and this is going to serve as a template for the, we'll find out whether or not what the implications for science were after the fact. My hope is in the scientific sphere, there's enough collaboration that a lot of those kinds of relationships can be kind of maintained. I mean, they, not necessarily directly through by law, but you can still have all of the policy boards and members and groups and things like that. But I guess as the funding percentages start to detach from one another, you're going to get to this place where they're going to have to come up with new methods of allocating funding, and then things are going to change.
Sure. I mean, in terms of the individual collaborations on specific projects, I think in the age of the internet that we live in, I mean, the four of us are sitting here in completely opposite corners of the world and are managing to collaborate on this project here. So I think in terms of individual collaboration, there won't be too much of a hit. But I mean, even here in the US, we're able to collaborate with fellow scientists in China despite the shaky US-China relations.
Yeah.
But like you said, it's the funding situation. It's also the opportunities for scientists to get involved and to apply for funding or grants or fellowships at all of the other amazing institutions that the EU hosts.
Well, we're just going to have to see how it plays out. So maybe a year from now, we'll see what the fallout was, and hopefully people will be working to fix it. So, okay, cool. So let's move on with Dave Dickinson. One final story, and then we wrap this up. Let's talk about a new all-sky meteor network.
Speaking of projects in Europe, this is something that was kind of interesting that they started up in France. Is the it's called Triton. It's the Fireball Recovery Interplanetary Observation Network, and this is a series of all-sky cameras that is fielded throughout the country with the idea of being able to rapidly recover spot bolides brighter than magnitude 0, triangulate their positions quickly, and actually have a series of volunteers, of professionals and amateurs and educators actually go out there and recover these meteorites. Now, there's other networks. NASA has an all-sky camera network in the US. There's one in Australia that covers a bigger area, but this one in France, it's particularly dense in that the cameras are only about 50 kilometers apart. So they're gonna, if there's a bolide over France, and there's actually some detectors they already have now in Spain, Sardinia, in Austria and Romania too. They want to spread this network out over Europe, but it's dense enough that several cameras are going to be able to see it, and they're going to be able to triangulate it down. This all works rather than having these cameras privately owned and on all these different disparate servers. These are all on one central server back at the Paris Observatory.
So, I mean, it's really interesting, right? You're going to have this coverage over a vast area of cameras that are constantly watching the sky, looking for those fireball events. They can start to get a much more accurate understanding of how often these events happen, which, as it turns out, is all the time, right?
Yeah. Yeah, they said that recovery-wise, it's about once a decade they have a fall over France that they actually recover. Strangely, and I don't know if there's any reason why this is, they said that it's gone down versus 19th century. Apparently, a lot of meteorites were falling on France because they said that they were recovering 1 or 2 a year, and this is before they had anything but Mark I eyeballs watching the sky for these sorts of things. So it's kind of, France kind of has a long history of meteor and meteorite recovery, which the French countryside isn't the best. You want to go somewhere like, say, the deserts down here in the Sahara or out in Antarctica, or somewhere where meteorites really stand out and contrast against like a background. So yeah, it's,
I've only seen one in my life. We actually did an episode of Astronomy Cast about 2 weeks ago about fireballs and bolides. And apparently Pamela set me straight that fireballs are when they're going through the sky, and bolides are when they land.
I watched that one, actually. I did watch you guys do that one. It was interesting. You guys discussed something that I've actually witnessed firsthand, electrophonic sound of actually hearing a hiss off a meteorite or off a fireball when they I've seen that kind of phenomenon too, and it is really kind of eerie. It's something that shouldn't be, but Japanese observers have actually recorded this before, and they know it's not a psychological phenomenon. It's a real they've had microphones actually pick it up. So it is a real phenomenon. It's interesting.
I can see how it would almost be psychosomatic. You know, you'd be seeing this thing in the sky that's bright and it's popping and crackling visually, and your brain would be going, I should be hearing video game sounds right now.
And it fills in, your brain fills in the gap. Aurora can do that too. There's been eyewitness accounts of people claiming that they've heard crackling noises from Aurora, and they think it's the same electrophonic sound phenomenon creating like a local disturbance.
Yeah. I mean, I think one of the, like with the Chelyabinsk event, this was, of course, that meteor that was really caught by all of those dash cams and stuff. I mean, this is like putting up a network of dash cams, but over a big wide area. It's pretty exciting. Cool. All right. Well, I think we've reached the end of today's episode and the end of this season of the Weekly Space Hangout. So let's give people a chance to let people know where they can find out more over the summer break as you are looking for news from all of the people. So let's start with Morgan. Morgan, where can people find out more about what you're doing?
Well, I hope you follow me on Twitter at Morgan Renberg. And if you're interested in anything I'm up to recently, you can visit me at morganrenberg.com.
Any planetarium shows coming up?
So we're also on summer hiatus, but we will be picking up again in the fall, and we have already putting together a great new series of shows for the fall season.
Fantastic. All right, Kimberly, where do people find out more?
Well, like Morgan, I hope you're following me on Twitter at AstroKimCartier. I'll be writing a series of blog posts on my website about my summer mentoring job that I have. So if you want to follow that, it's at kimberlycartier.org. And if you happen to be in the central Pennsylvania area around mid-July, the Penn State Astronomy Department hosts an event called AstroFest. It's our biggest public outreach event of the year. So if you are around Pennsylvania or are willing to make the drive, come stop on by because it's a fantastic series of evenings.
Awesome. Dave Dickinson.
Yes, I'm Astroguides with a Z, and I will stay active writing about what's up in the sky in Universe Today, Sky and Telescope, and I'm also writing about our adventures of being homeless, traveling and writing in Morocco. Part of our rough plan, once our 90-day visa runs out here, is to head over to Tunisia. We're long-term traveling. We're not really on vacation. We're just traveling and writing. So,
fortunately, you can do your job from afar. So
as long as we get Wi-Fi.
Yeah, once you get Wi-Fi, you're able to do your job. Well, you are definitely an inspiration to all of us who have those aspirations of traveling the world. I think once the kids.
We're paving the way and trying to make the Wi-Fi better for everybody out here. So.
Yeah. Well, great. Thank you. Yeah, you should leave a trail of good and bad. Or what are all the good Wi-Fi spots so that the rest of us can join you. So now the next kind of big thing that we're going to be doing. Obviously, we'll be returning in the fall. I know Pamela's going to be going to DragonCon to do a bunch of live stuff there. We'll probably do a live astronomy cast, or she will, and they'll probably have something for the Weekly Space Hangout from there. We'll definitely be returning the week after Labor Day, after DragonCon. Let's see who's gonna be going. So Morgan, probably Sandy, and perhaps some others. Pamela are all going to be at the OSIRIS-REx launch as well, and that's in early September. So hopefully we're going to do a bunch of fun live stuff from Cape Canaveral, and maybe I'll get a chance to watch my first rocket launch. So that'll be then. Cool. All right. Well, so if you enjoyed this show, please give it a thumbs up. There's some thumbs up battling to be done. So definitely give it a thumbs up and let us know if you enjoyed it. If you haven't already, subscribe to this channel, and that way you'll get all of the announcements when we come back from our hiatus. A big thank you, as always, to all of the guests that we had this entire season. It was a great run of guests, and I really hope that's going to sort of set the standard for what's going to happen for the next the next year when we return. A big thanks to Chad, of course, my engineer, for helping us make this transition to new software just in time to abandon it for a couple of months, but we learned a ton, and I hope this episode was really smooth. And it was great. A big thank you to all of the WSH crew. These are the dedicated fans who have been here week after week, helping us put these shows together, stay sane, battle trolls, and really kind of make the show better. And I think, this collaboration between us as the show and the fans of the show is something really special. And I'm really looking forward to sort of investigating how we can go even deeper on making letting the people who enjoy the show really be in control of the show that they get to see. And, you know, I am happy to really give the keys to this group of people and let them just drive. And I'll just be a passenger. And so you know, it just means a lot to me that there's this group of people that's this dedicated and this excited. And the more that I can give back to you to help you get the show that you want to see, the better we can do. So thanks again to everybody for a great season. Thanks to, man, I'm all out of thanks. We will see you all. One last reminder, we're going to be doing Astronomy Cast in about 10 minutes. So you may want to go over to the Astronomy Cast channel where you're hearing me say all this stuff again. And don't forget to watch The Guide to Space. And we'll see you all in September.
End stream?
End the stream.